Hello, everyone. Today we are taking a closer look at the open source YOR project. That's YOR, which stands for Your Own Robot. YOR is an open source mobile manipulation platform built from commercially available robotics components. It combines an omnidirectional base, a telescopic lift, two robotic arms, custom grippers, onboard computers, sensors, and an open source software stack. In this video, we will break down the major components that make up YOR and explain how they work together as a complete robot. At the bottom of YOR is a custom aluminum chassis built around 4 Robotics 3-inch max swerve modules. A swerve module is more complex than a normal powered wheel because it contains 2 separate motors. A Neovortex brushless motor drives the wheel forward and backward. A smaller Neo 550 motor connected through an ultraplanetary gearbox rotates the entire wheel assembly to control its steering angle. Because all 4 modules steer independently, YOR can translate sideways, move diagonally, rotate in place, or combine rotation and translation in a single motion. The controller calculates the required steering angle and wheel velocity for every module based on the desired movement of the chassis. It also uses a shortest turn optimization. When rotating a wheel toward the requested angle would require more than 90 degrees of steering, the controller reverses the wheel's drive direction and targets the equivalent opposite angle. This reduces steering delay and mechanical wear. The chassis itself is assembled from dense aluminum extrusion. The battery, the computer, the voltage regulators, and power distribution hardware are mounted low and near the center of the base. This is a deliberate choice. The lift and arms place significant mass above the chassis, so concentrating heavy components near the floor lowers the robot's center of gravity and increases its resistance to tipping. The wheels are also positioned near the outer corners, creating the largest practical support polygon within YOR's compact footprint. The 4 swerve modules represent roughly $2,700 of the robot's bill of materials before including the aluminum frame and mounting hardware. Mounted on the base is a telescopic lifting column originally designed for an adjustable standing desk. Instead of developing a custom linear actuator, the YOR team selected an existing lift because it already provides mechanical rigidity, a long vertical stroke, and the ability to support a large offset load. The lift is also self-locking. If electrical power is lost, the upper body should not suddenly drop under its own weight. A Raspberry Pi Pico acts as the lift controller. It reads the column's encoder to determine its current position, then controls the lift's DC motor through a BTS 7960 high current H-bridge. Using pulse width modulation, the Pico can regulate both the lift's velocity and its final height rather than simply switching it fully on or off. YOR uses 2 AgileX PiPER robotic arms. Each PiPER arm has 6 controlled joints, giving it 6 degrees of freedom for positioning and orienting its end effector. Each arm weighs approximately 4.2 kilograms and costs around $2,500, meaning the pair accounts for more than half of YOR's total hardware cost. The arms are not mounted vertically. They attach to a custom sheet metal shoulder plate that angles each arm outward by approximately 45 degrees. This angle improves forward and downward reach while keeping the shoulders close together. It also directs the elbows away from each other, reducing the chance of collisions between the arms during bimanual movement. That allows YOR to retain a narrow body while still providing two useful manipulation workspaces. The PiPER arms communicate over a CAN bus. At the software level, YOR supports both direct joint space commands and task space control, where the user or policy specifies a desired end effector pose, and inverse kinematics calculates the required joint positions. The arms are controlled using a joint stiffness strategy rather than completely rigid position control. Conceptually, each joint behaves like a programmable spring and damper around its target position. Gravity compensation supports the weight of the arm, allowing the stiffness gains to remain relatively low. That means the arms can yield when they encounter an object or external force instead of fighting aggressively to maintain an exact position. The low-level ARM controller runs at 200 Hz and uses Ruckig trajectory generation to keep movements within defined velocity, acceleration, and jerk limits. A slower high-level controller provides the target joint positions or task space poses. This compliance is particularly valuable during teleoperation, learned policy deployment, and contact-rich tasks where small positioning errors are inevitable. At the end of each arm is a custom gripper driven by a Dynamixel actuator. The grippers use angular jaws rather than simple parallel fingers. That geometry is intended to support both precise grasping and stronger force application when holding or pressing against larger objects. Each gripper also incorporates an iPhone as an off-the-shelf sensing package. The Dynamixel motors are connected through a USB interface and power hub, allowing the main computer to command and monitor the grippers. The standard onboard computer is a Raspberry Pi 5 with 16 gigabytes of memory and an active cooler. The Pi runs the main robot control software, communicates with the arms through CAN bus, sends commands to the mobile base and lift controller, and connects to peripherals through USB and Ethernet. A powered USB hub expands the number of available interfaces. The Raspberry Pi Pico handles the lift's real-time encoder and motor control loop, separating that task from the main computer. For teleoperation, the standard parts list also includes a wireless gamepad. For heavier perception and autonomous navigation workloads, the research platform can also use an NVIDIA Jetson Orin alongside a Z2i stereo camera. All of these systems are powered by a central battery mounted inside the base. A power distribution board routes energy to the different subsystems, while several DC to DC regulators convert the battery voltage into the levels required by the arms, computers, sensors, and control electronics. The parts list includes two 24 to 24 volt regulated outputs, one 24 to 12 volt converter, and one 24 to 5 volt converter. An emergency stop switch provides a physical method of interrupting the system during testing or unsafe behavior. Cable carriers, terminal blocks, Anderson connectors, Wago connectors, crimp terminals, and separate wire gauges manage power and signals as the lift and arms move. All of these parts are visually unremarkable, but they are essential to making a moving robot reliable. YOR is inexpensive because it combines mature components in a practical architecture. A standing desk column provides vertical reach. Two PiPER arms provide bimanual manipulation. The published bill of materials totals approximately $9,200 for the base configuration. YOR's most interesting engineering achievement may not be any single component. It is the way those components have been integrated into one compact, reproducible, mobile robot. Alright, if you like this content, subscribe. That's how you can help the channel out. That's how you can help the channel grow. And leave a comment below. Let me know if you would build this robot. Let me know what you might do with it in the comments below. And I'll catch you in the next one. That's all, folks.